We live in an era where technology is advancing at an unprecedented pace. Artificial intelligence stands as a testament to this progress, permeating various aspects of our lives. AI encompasses a broad spectrum of techniques that empower machines to mimic human intelligence. Among these techniques, deep learning emerges as a powerful force, driving innovation across industries. From self-driving cars to personalized medicine, deep learning is transforming our world in profound ways. Deep learning's ability to analyze vast data sets and extract meaningful patterns has enabled breakthroughs in fields such as computer vision, natural language processing, and robotics. Its applications are wide-ranging, impacting healthcare, finance, transportation, and entertainment, among others. Understanding deep learning is crucial for comprehending the current technological landscape and envisioning the possibilities that lie ahead. Deep learning represents a specialized subset of machine learning. Machine learning, in essence, involves training algorithms on data to enable them to make predictions or decisions without explicit programming. Deep learning takes this concept a step further by employing artificial neural networks. These networks are inspired by the structure and function of the human brain. Traditional machine learning algorithms often require human intervention to extract relevant features from data. Deep learning, on the other hand, automates this feature extraction process. It achieves this through its multi-layered neural networks, which learn hierarchical representations of data. This ability to learn complex patterns from raw data makes deep learning particularly well-suited for tasks involving unstructured data, such as images, audio, and text. Neural networks serve as the backbone of deep learning. These computational models consist of interconnected nodes, or neurons, organized in layers. Each connection between neurons has a weight associated with it, which determines the strength of the connection. The network learns by adjusting these weights based on the input data it receives. The input layer receives the raw data, such as pixels in an image or words in a sentence. This data is then processed through one or more hidden layers. Each hidden layer performs a series of computations on the input data, transforming it into increasingly abstract representations. Finally, the output layer produces the network's prediction or decision. The depth of a neural network refers to the number of hidden layers it possesses. Deep learning networks typically have multiple hidden layers, hence the name deep learning. Each hidden layer learns to detect different features or patterns in the data. For instance, in image recognition, the first hidden layer might detect edges and corners, while subsequent layers might identify more complex shapes, such as circles or squares. The final hidden layers would then learn to recognize even more abstract features, such as faces or objects. This hierarchical feature learning allows deep learning models to achieve high accuracy in complex tasks. Section 5. Deep Learning in Action. From image recognition to language translation. Deep learning has found applications in a myriad of fields, revolutionizing the way we interact with technology and the world around us. One prominent example is image recognition, where deep learning algorithms power applications like Google Photos, which can automatically tag and categorize images based on their content. Voice assistants, such as Siri and Alexa, rely heavily on deep learning for speech recognition and natural language processing. These assistants can understand our spoken commands, answer questions, and perform tasks, such as playing music or setting reminders. In the realm of transportation, deep learning is the driving force behind autonomous vehicles. Companies like Tesla utilize deep learning algorithms to enable cars to perceive their surroundings, make decisions, and navigate roads without human intervention. Section 6. The Deep Learning Process. A journey from data to insights. The deep learning process involves a series of steps that transform raw data into meaningful insights. The first step is data collection, where vast amounts of data relevant to the task at hand are gathered. This data is then pre-processed to clean and format it for training the neural network. Next comes the model training phase, where the neural network learns from the pre-processed data. The network's weights are adjusted iteratively to minimize errors between its predictions and the actual values in the training data. Once the model is trained, it undergoes evaluation on a separate dataset to assess its performance. If the model performs well, it can then be deployed to make predictions on new, unseen data. Section 7. Challenges in the Deep. Navigating the complexities of deep learning. Despite its remarkable capabilities, deep learning faces several challenges. One significant hurdle is the requirement for massive datasets. Deep learning models typically need vast amounts of data to learn effectively. Obtaining and labeling such large datasets can be time-consuming and expensive. Computational resources present another challenge. Training deep learning models, especially large and complex ones, demands significant computational power. This often requires specialized hardware, such as GPUs or TPUs, which can be costly. Section 8. The Ethical Implications. Addressing bias and fairness in AI. As deep learning becomes more pervasive, it is crucial to address the ethical implications associated with its use. One concern is the potential for bias in AI systems. If the training data reflects existing societal biases, the resulting model may perpetuate and even amplify these biases. For instance, a facial recognition system trained on a dataset predominantly composed of light-skinned faces may perform poorly on darker-skinned faces. This could lead to unfair or discriminatory outcomes. Ensuring fairness and mitigating bias in deep learning models is essential for building responsible and equitable AI systems. Section 9. The Future of Deep Learning. A glimpse into the possibilities. The field of deep learning is constantly evolving, with new breakthroughs and applications emerging at a rapid pace. Researchers are exploring novel architectures, training algorithms, and techniques to enhance the capabilities of deep learning models. One area of active research is explainable AI, or XAI, which aims to make deep learning models more transparent and interpretable. This is crucial for building trust in AI systems, especially in critical domains such as healthcare and finance. Another promising avenue is the development of more efficient deep learning models that require less data and computational resources. Section 10. Conclusion. Embracing the potential of deep learning. Deep learning has emerged as a transformative technology, driving innovation across industries and shaping the future of AI. Its ability to learn complex patterns from data has enabled breakthroughs in areas such as image recognition, natural language processing, and robotics. While challenges remain, the potential of deep learning is vast. By understanding the fundamentals of deep learning, addressing its challenges responsibly, and embracing its potential, we can harness its power to create a better future. As deep learning continues to evolve, it holds the promise of solving some of humanity's most pressing problems and unlocking new frontiers in science, technology, and beyond.